Okay, this is a demonstration of doing Bonferroni correction for multiple comparisons as part of a Oneway ANOVA test in Excel. And we are comparing more than two means here. So you can see we've got four different means that we want to compare. Bonferroni correction is a more stringent method of correcting for multiple comparisons. The Fisher's LSD test is another one you can view in another video, and that doesn't give you a whole lot of correction for your alpha, so it's really suited for when you're not doing a whole lot of comparisons. A good rule of thumb is 3 or less comparisons. You can use the Fisher's LSD test. If you're performing more than 3 comparisons, then some other method is probably good. We'll demonstrate how to do Bonferroni correction. There are other methods out there as well. So the first thing to do is to run your Oneway ANOVA. So we go to Data Analysis, Tool Pack, ANOVA Single Factor. We're going to select all of this data. Make sure we get all of the numbers included, even though there's kind of a raggedy edge because of the unequal sample sizes. These are approximately equal sample sizes, so it's fine. Data is grouped by columns. And now let's select the output range. It's right here. Okay, so there is our output, and you can see this is significant. We've got a very small p-value here, a large F statistic, and so this allows us to reject the null hypothesis that all the means are equal, but now we still need to determine where does the difference lie, where does the difference actually exist. And interestingly, for Bonferroni, you don't actually have to have a significant F statistic in order to proceed and do the multiple comparisons. I don't understand all of the math behind it, but it is possible to get a non-significant F and still get a significant pairwise comparison between a couple of your means. Probably has to do with just the power of each test, the power of the F test versus power of a two-sample T-test, which we'll do in just a sec. Excuse me. But yeah, this is still something that is typically going to be reported. The ANOVA test, just doing the omnibus test to see if there's a difference anywhere, to see if there's an effect of group membership on this dependent variable. Okay, so now we've got 4 means, and here I've sketched out this little table to show you all the possible comparisons that can be made. We've grayed out this diagonal, and then doing all these represents all the different comparisons, so we can gray out the rest here. So there are 6 different comparisons that can be made. Now, not all of these comparisons may be scientifically relevant. They may not be relevant to your research question. Maybe, for example, the group A is a control group, and you just want to know which of these 3 treatments, B, C, or D, is different from the control condition. And so you may not really want to compare the treatments with each other at this point. Maybe you just want to see which one is different from group A. And so in that case, you'd only be interested in these 3 comparisons. So that's something that you need to decide beforehand, which comparisons are actually meaningful to you. Now let's say for the purposes of this demonstration that all 6 of these are meaningful, that we're interested in all 6, and we want to run all of these tests, which are going to be t-tests. We're going to need to correct for that inflation of alpha, and the Bonferroni method is to divide your alpha by the number of comparisons that are performed. So it's a pretty straightforward calculation. You just take, let's say our alpha is 0.05, which is typical, and you divide it by 6. So you get 0.08333. Okay, so now we're going to do a bunch of t-tests, and you're going to need to find a p-value that is less than 0.008 in order to declare a result to be statistically significant, as opposed to just less than 0.05. Okay, so here I've it's a good idea to keep things organized and well labeled when you're doing these types of tests, because there's kind of a lot going on. We can just use the Ttest function here, and we can select, here's A versus B, so array under group A and then under group B. And this we're going to do a two-tailed t-test. Our typical alternative hypothesis is just that one mean is different from some mean is different from some other mean, and so there's not really a direction associated with that. So we'll just use the two-tailed distribution, and then we're going to do the two-sample with equal variance. Now, why do we use equal variance? Well, that's an assumption for using the ANOVA test. The variances are approximately equal. So if we've determined that they're not, then we should be doing some other test besides ANOVA. Okay, close parentheses, and there we get our p-value, which is very low. And you can maybe save a little time by pasting the formula and just repeating the test after adjusting the input. Here's A versus D. Make sure we expand that to get that number 4. So this is where it gets a little tedious just to do a whole lot of t-tests over and over again. Excel is not the best tool for this because there are softwares that will just do all this for you. But Excel requires a little bit more work. So B versus D. And last but not least, C versus D. Select C for that, and D for this one. Okay, so now we've got our 6 p-values now, and we will indicate which ones are statistically significant and which ones aren't. Now don't get thrown off by the 2.28. This is 2.28 times 10 to the minus 5, so that's 0.0000028. So this is a very small number. This is definitely smaller than 0.008. Okay, so we'll highlight that one. This one is similar in magnitude. So is that one. 0.32 is, we wouldn't even declare that statistically significant if we weren't using Bonferroni correction, as well as that one and that one. Okay, so A versus B, B versus C, and B versus D are statistically significant from each other. Significantly different from each other, so that's what you would report. Typically you would report, the results of your ANOVA, and then say that you performed these pairwise comparisons using Bonferroni correction, and these were the results that were statistically significant, reporting the t-statistics from these t-tests and the values. Now, just so you're aware, for for example, other softwares, they might use a slightly different t-test than the two sample t-test. So you might get slightly different results if you're running a different program, but they're going to usually be pretty similar. And Bonferroni correction is used for just doing multiple t-tests like this too. And since you don't even need a significant f, this is a way that you could do your multiple comparisons with just that regular two sample t-test. All right.